Thank you, and all participants expressed their acceptance, so I would like also to express my gratitude to organizers to invite me here and to meet a nice group of my colleagues. It is my 6th visit to Yerevan, so my last visit was 7 years ago, so I am happy to be here again. So I will speak about application of the potential method to transmission problems for composite layered elastic structures containing interfacial cracks. And the main tool will be the potential method and the theory of pseudo-differential operators on manifolds with boundary. This is the joint work with Buchukuri and Chkadua from Tbilisi State University. And this investigation was carried out under the grant of Shota Rustaveli National Science Foundation of Georgia. We are happy that we have this kind of possibility to get grants from this foundation. So you see here the plan of my talk. First and the second item, it is related to the physical field equations of the general thermoelectromagnetic elasticity theory, fully coupled Green-Lindsay model. I will formulate the boundary transmission problems, introduce the corresponding differential operators, boundary operators, and give rigorous formulation of the mathematical problem. Then I will investigate the well-posedness of the problem with the help of the potential method. I need properties of potentials in the closed domains. The case is that usually in this kind of mixed and crack boundary type problems, we have not regular solutions, so we need to investigate the problem in the generalized function spaces. So by the potential method, we reduce the transmission problem to corresponding pseudo-differential equations, and after establishing that these operators generated by these boundary integral operators have some special Fredholm properties, we need also to find out what happens near the so-called exceptional curves. Exceptional curves, usually there are edges of cracks and the collision curves where the different types of boundary conditions collide, for example, Dirichlet type to Neyman type and so-called. And finally, the important problem is how to find the singularities of the mechanical, electromagnetic, and thermomechanical fields near these exceptional curves. And the most important thing is to characterize the singularity exponents for stresses, which are related to the first-order derivatives of solutions, and usually, in contrast to the standard interior cracks, we consider here layered structures, and crack is along the interface, so they essentially depend on the material parameters, and we will try to formulate how to find them and give some algebraic scheme how to find numerically them. Okay, to start now the problem. So some notations. U will be displacement vector, three-dimensional, U1, U2, and 3. Phi and psi are electric and magnetic potentials, theta the temperature distribution, and you see here the thermomechanical and electromagnetic fields, epsilon kj, the mechanical strain tensor, this is the mechanical stress tensor, E stands for the electric field, H for the magnetic field, dB, they denote the electric displacement vector and magnetic induction vector, Q is the heat flux, S is the entropy, and I already told you I will consider the fully coupled theory, which means that all these fields, thermomechanical and electromagnetic fields, are related by these constitutive relations. And since I already told you that I will consider the generalized fully coupled Green's model, in the classical theory we have not these kind of terms which finally lead to the hyperbolic type equations, in contrast to the standard classical field where we have the parabolic character of the corresponding functions. The material parameters here, they satisfy some standard symmetry properties and satisfy conditions with guarantee that the corresponding energetic quadratic form is positive definite. So as I already mentioned, the additional terms which I showed there, they lead to the so-called second sound effect, which means that temperature is distributed now by finite speed, in contrast to the classical theory when we have the infinite distribution for temperature. Okay, so we have the following field equations, which is equation of motion, quasi-static equation for the electric and magnetic fields, the linearized theory, linearized energy equation. And if we now unite these field equations together with the equations which was shown here with constitutive relations, then we can write all these equations in the form of system of partial differential equations. But this is not standard system of partial differential equations, because the first three equations and the sixth one, they have the hyperbolic character, while the fourth and fifth equation, they have the elliptic structure, because they don't contain the derivatives with respect to time parameter t. So the corresponding initial boundary value problems should be specifically formulated here. If we use the standard Laplace transform, where tau is the complex parameter with sigma positive, then this dynamical system can be reduced to strongly elliptic system of partial differential equations. And if we denote by capital U the corresponding 6 vector, then it can be written in the form of matrix form, where psi is known right-hand side 6 vector, and U is, as I mentioned, strongly elliptic but not self-adjoint matrix differential operator. To formulate the mixed boundary transmission problem, we need also to introduce the corresponding generalized stress vector, which is boundary operator containing the first order derivatives on the boundary. N stands for the unit normal vector to the boundary. And the sense of this boundary operator is the following, that if we apply the operator T to 6-dimensional vector U, the first 3 components correspond to the mechanical stresses. The fourth one and fifth one, they are normal components of the displacement, electric displacement vector and magnetic induction vector. And the final 6th component, this is the normal component of the heat flux vector. So about the geometry, what we will consider. Usually we can consider the arbitrary layered structure, but I will consider only now the composite body, which contains the interior domain omega 1 and omega 2. And I assume that these regions are filled by materials which have the corresponding properties which was described above. And so the exterior boundary S2 is divided into 2 parts, S2n, the so-called Neumann part, where the stress vector will be prescribed, and S2d, where the Dirichlet condition is given. That means that the vector capital U will be given here. The interface surface is divided also into 2 parts, S1t and S1c. S1t correspond to the rigid contact conditions manifold, and S1c is just the crack surface. And there will be given crack boundary conditions. So all mechanical and electromagnetic fields and also coefficients will be equipped by the superscript m corresponding to the domain omega m. And so we can now formulate the basic boundary mixed boundary transmission problem, but I would like to say that the collision curves L1 and L2, L1 is the crack edge and L1 is the collision curve and L2 is the crack edge. So at this, as I mentioned, there arise singularities, and our main goal in this investigation is to characterize the appropriate proper functional spaces, which gives us also the asymptotic near these exceptional curves. So I will use the standard Lebesgue, Sobolev-Slobodetsky, Bessel potential and Bessel spaces. And by tilde, I denote those spaces for M is the proper submanifold of the closed manifold S. Tilde means that they are supported on the closure of the manifold M. Without tilde, they are just spaces of restrictions. Now we are ready to formulate the main problem. Rigorous formulation of the problem is the following: that we are looking for pair of vectors u1 and u2 from this Sobolev space for p greater than 1, satisfying the differential equation in the corresponding domain omega 1, the Dirichlet conditions on the boundary S2D, Dirichlet part I showed you, and Neumann part on the exterior boundary, transmission conditions on the transmission part, rigid transmission conditions, you see, rigid contact conditions, and interface crack conditions from the both sides of the crack. There are given the generalized stress vectors. Usually in the physical fields, maybe they will be 0, but depending on what is the intermediate part, maybe there will be isolated thermally isolation, or maybe some different properties can be found here, can be prescribed here. So the right-hand side, the data of on the boundary, they meet the special conditions which comes from the generalized trace theorem or the standard trace theorem, because you see that here are negative Bessel spaces. So this comes from the generalization, because the stress vectors in the standard way, we have not trace for those vectors, and we define them by Green's function, and it can be shown that this is well-defined. The stress, generalized stress for stress vector is well-defined, and so the data where the stress vector is prescribed, they belong to this negative exponent Bessel spaces. By standard way, it can be shown that in the case when p equals to 2 in this Sobolev spaces, the problem has at most one solution, which means that the homogeneous problem has only the trivial solution. To prove the existence theorems and the corresponding regularity theorems, we need to apply, as I mentioned already, the potential method. So we denote by psi k, the psi m, the fundamental solution of this strongly elliptic differential operator. We investigate the properties of this. It can be constructed by Fourier transform, and only in exceptional cases we can only construct explicitly those entries of these matrices. Then we construct the single layer potential, which is integral on the boundary S. The kernel, due to this, is weakly singular. We consider the three-dimensional problems. I forgot to take. So S is two-dimensional boundary. And so this is weakly singular kernel in this case. And so this is the single layer potential, where S will be either S1, the exterior boundary, or S2, the interior boundary. Next, we introduce the integral operators, boundary integral operator generated by the single layer potential. It is the direct value of the single layer potential on the boundary S, and Ks is the direct value of the single layer potential of the stress operator applied to the single layer potential. This is the weakly singular integral operator, while this is a Zygmund type singular integral operator. We use the standard jump relations. Single layer potential is continuous across the surface S, and so it generates the operator HS. And the T operation applied to single layer potential gives the jump relation, which is half of the density of H, depending on the limit is taken from the inside or outside, minus or plus there. And so we have the following mapping properties between these Bessel and Besso spaces. And it must be mentioned that HS is smoothing operator. As you see, the R parameter R is increased by 1, while this operator preserves the space as a singular integral operator, and these operators can be considered as pseudo-differential operators of order -1 and of order 0. For arbitrary P and Q, they have this property. But I would like to mention here that if S is infinitely smooth, then you see the whole spectra of parameters. But if S is Lipschitz, which is also in our framework, then we can restrict the smoothness of the corresponding operators of the corresponding spaces, because on the Lipschitz surface we can define maximal smoothness when the smoothness parameter equals to 1. Moreover, this operator is invertible for arbitrary values of this parameter, while this operator is Fredholm operator with 0 index. And finally, the mapping property of the single layer potential. This is also smoothing operator, as we see, and smoothing index is 1 plus 1 over P, which indicates equals to 2 is 3 over 2. So we have these properties. And okay, so the first principal thing was here how to look for solution for this very complex mixed boundary transmission problem. We found that U1, which is in the domain omega 1, and U2 in the domain omega 2, can be represented in the form of single layer potential with special density here, and here also the densities are specially constructed. These operators P1, P2, and R2 are constructed explicitly, but they contain some inverse integral operators on the boundary. But you will see also some inverse operators in my analysis, but sometimes they are not sometimes, almost every time, we have not explicit expression for those operators, but it turned out that the homogeneous principal homogeneous symbols we can write explicitly, and this plays crucial role for our goal to find what are the singularities and regularities of solutions. So using this representation, the Dirichlet data are automatically satisfied. The rigid transmission conditions also are automatically satisfied, and we need also to satisfy only Craig type conditions and Neumann type condition on the exterior boundary. That's why we have here only two unknown densities, H and G. They belong to these tilde spaces, and so we have to find those densities and the problem will be solved. So to apply the properties of the single layer potential, what I just mentioned there, the problem is reduced to the pseudo-differential operator, pseudo-differential equation here, where n is the blockwise this matrix differential pseudo-differential operator with blocks P, which is expressed here, and AS, and they are the generalized Steklov-Poincaré type operators. Just these inverse operators, as I mentioned, are not available explicitly, but their symbol matrices can be written explicitly. Okay, this summand B is compact perturbation for the operator N, and if we introduce the corresponding spaces, direct product of the Bessel spaces, this operator has this mapping property from X to Y space for arbitrary parameters. As I mentioned, B is between these spaces compact operator, but unfortunately this operator is not invertible for arbitrary parameters what are written here, and characterize this mapping property, and to find out the exact range for these parameters P, Q, and R for which this operator will be invertible, we use the Vishek-Eskin approach to solve the pseudo-differential equations on manifolds with boundary, and that's why we need to introduce to construct special matrix D1 and D2, which are related to the principal homogeneous symbol matrix of P and of the operator A2. As I mentioned, these symbols can be written explicitly, and so we need also when X belongs to the crack edge and to the collision curve. After that, we have to find these numbers which are related. Okay, so I have to mention that lambda 1j, we denote the eigenvalues of this matrix, and lambda 2j, the eigenvalues of this matrix. They play a crucial role in the asymptotic properties of solutions. And we find the gamma 1 prime and gamma 1 2 prime as the infimum supremum of the arguments of these eigenvalues. Similarly, this gamma 2 prime and gamma 2 prime, and then choose the minimum between gamma primes and gamma 2 primes. And we showed that gamma prime is non-positive but greater than -half, and gamma 2 prime is less than half but non-negative. And this is the result that the corresponding pseudo-differential operators involved in the equations, they are strongly elliptic as well. So if now we choose the parameters R and P satisfying this inequality, then this operator is invertible for arbitrary values of P and R which satisfy this, for arbitrary Q, by the way. So this operator is invertible. This immediately then leads to the existence result to the basic original problem, transmission problem. And if P satisfies this inequality, where gamma prime and gamma 2 prime are explicitly found, then we have the unique solvability of the mixed boundary transmission problem in those spaces. And it should be mentioned that when P equals to 2, this value of the parameter always belongs to the space, and this gives us possibility to consider the Lipschitz case as well. And so in the case of Lipschitz surfaces, which may contain angles and so on, this is not smooth surface. That's why we have the existence only in the case when P equals to 2. Unfortunately, in this case, we cannot say anything about singular behavior. They belong only in those spaces. But for regular surfaces, we have the following regularity result. That assume that the boundary data are even C infinity, and also geometry is C infinity. The solution belongs to intersection of all Holder spaces with exponent alpha prime, where alpha prime is less than kappa, and kappa is the minimum between alpha. This is the regularity exponent for the boundary data, and gamma prime plus half. But since gamma is non-positive, so the maximal possible regularity is C 1/2 minus epsilon, where epsilon is an arbitrary small number. Okay, I will omit the proof of this. And now concerning the asymptotic of this. Concerning the asymptotic, the case is that if we denote by dx the distance from the reference point x to the exceptional curves L1 or L2, we found first the asymptotic for the solution of the pseudo-differential equation for the densities h and g involved in the equations, and then derive the three-dimensional asymptotic near the exceptional curves. And you see this looks like this distance to the power gamma jk plus I times nu jk, where these parameters gamma and nu are evaluated by the arguments of the above mentioned eigenvalues of the corresponding matrices. G here is good function, which is function of x prime, where x prime belongs to L1 and in union L2. So as I mentioned, this is sufficiently smooth function. So the main singularity is here, and also here is involved beta jk, which is the multiplicity of the eigenvalue A, and if they are just simple eigenvalues, then this equals to 0, and so we have not logarithmic term in this case. In some cases, when we have the pseudo-differential operator with the pseudo-differential equation with positive definite symbol, then also beta equals to 0, so no logarithmic terms there are. And finally, now if you evaluate the stress operator from the solution vector functions, then due to the first order differentiation of the operator tau m, we have this kind of singularity there, and these exponents are called stress singularity exponents. And now we see that if the modulus of lambda j k is different from 1, then we have here the oscillating singularity, which is very dangerous from the mechanical point of view. And also this makes contradiction to the linear theory, because it leads to the overlapping of materials. So this shows that sometimes when it is very, very dangerous, we have to avoid somehow to this oscillating singularities. Finally, we have some, for some particular cases, calculated those singularity exponents. And this topic was started in the Stuttgart University maybe 15 years ago. There was a project. We just, these 3 persons, authors of this investigation, we are involved there. That was Bosch company project. And the similar result was obtained there. L1, this is the crack edge. L2 is the collision curve, where Neumann type condition and Dirichlet type condition collide. And this was a very unexpected result, that at the crack edge singularity is less than singularity at the collision curve. But we considered this topic with engineers in Stuttgart University at the time, and they say that sometimes it happens, and so we don't know whether really this is case, because mathematical calculation gives this result. So I think that this is that. You see some papers here where this was. So thank you very much for this.